presentation is a series of excerpts from a tutorial I wrote for my colleagues at work. The tutorial also serves as the capstone project for the bachelor's degree program at Grantham University. Hello, my name is Bob Jones. The purpose of my project is twofold. One, to discuss concepts that are relevant to the product supported by the service staff and my employer, Rodian Schwartz. And two, to improve the skills of service staff members, particularly the newer people. The reason I chose this project is that earlier this year I was given the responsibility of addressing the lack of service training and asked to develop a tutorial. Realizing I was going to do a lot of the work at home, I decided to see if I could use the project to meet the requirements of the project management and capstone project courses. The important lesson I learned is that I should have chosen an electronics device as my project instead of the training tutorial. Although my project will benefit dozens of employees within my company, the capstone project course is structured for an electronics design project, and that's what I should have done. Originally, my target date for completion was July 24th, which is the final day of the course. The project is on schedule to meet that deadline. However, it may be pushed forward a little bit to meet the requirements of week 7 of the capstone project course. This presentation consists of selected excerpts taken from my project tutorial, which have been edited for this presentation. It is assumed all readers have some formal classroom training in electronics, such as college, military school, or technical school. And it uses mathematics only to the extent required to adequately illustrate the concept. Overviews of 7 topics are presented: units of measurement, impedance, maximum power transfer, VSWR, noise, mixers, and phase lock loops. The project tutorial includes 8 other topics, but this presentation is designed to show representative examples of my project. The complete project document will be submitted along with this PowerPoint presentation sometime during the final 2 weeks of this course. Units of measurement. Everyone who's been in electronics for a while has heard the term dB. But what is a dB? dB is short for decibels, which is a tool developed by Alexander Graham Bell to simplify the comparison of 2 widely different power or voltage levels. By itself, dB is not a unit of measurement like watts or volts. It's only a ratio of one value to another. In electronic circuits and systems, dBm is widely used, meaning decibels with respect to 1 milliwatt. Another common term is dBc, which means decibels with respect to another signal, usually called the carrier. Unlike a linear or direct ratio, dB is used to quantify a logarithmic ratio. It provides a convenient way to compare vastly different values using a small number. For example, the linear power ratio of 1,000,000 to 1 is the same as a logarithmic ratio of 60 dB. The math relationships are quite simple. For power, multiply 10 times the log of the power ratio. For voltage, multiply 20 times the log of the voltage ratio. In this case, log refers to log of base 10. Impedance. The combined effects of resistance R and reactance X gives us impedance Z, where in its simplest form Z would be equal to R plus X. The unit of measurement is ohms. Impedance is a characteristic of both inputs and outputs. The industry standard is 50 ohms for most high-frequency devices. Television systems use 75 ohms. Smaller resistances provide advantages, especially at high frequencies, such as wider bandwidth and lower noise levels. At very low frequencies and under ideal conditions, the load resistance passes all the signal current and dissipates the entire power transferred from the source. maximum power transfer theorem states that the maximum amount of power transferred from the source to the load can only occur when the load impedance matches the source impedance. Any variations in the load impedance, either above or below the 50 ohm source impedance, causes reduced power to be dissipated in the load. In the example shown here, the theoretical maximum power that can be transferred to the load resistance is 13 dBm. If the load resistance changes to values above or below the source impedance, the load power is reduced. In addition to changes in the load impedance, other considerations come into play as frequency increases. Because every connection, even a short wire or circuit run, takes on inductive and capacitive reactance characteristics as the signal frequencies increase. At some point, the reactive elements affect the power transfer such that some signal voltage is dropped across parasitic inductance and some signal current flows through stray capacitance, and therefore less power is transferred to the resistive load. VSWR. As voltage is applied from the source to the load, we call that the incident voltage. Some voltage is reflected back after it is applied to the resistive load and is reflected back toward the source. That's called reflected voltage. The reflection is caused by a mismatch between the load and source impedances. The ratio of the reflected voltage to the incident voltage is called the reflection coefficient. In electronics, we use the Greek letter gamma, which is always 1 or less. If all of the incident energy is reflected, the coefficient is 1. Otherwise, it's less than 1. The reflected voltage is added to and subtracted from the incident voltage at regularly spaced points along the line. Those points are stationary or standing. The addition and subtraction of the incident voltage by the reflected voltage creates maximum and minimum voltage levels called Vmax and Vmin. The ratio of Vmax to Vmin is the voltage standing wave ratio, or VSWR. VSWR is a measurement or a quantification of the quality of impedance matching between the source and load. Also, VSWR can be expressed as a logarithmic ratio, which is often called return loss. For voltage, the return loss is 20 times the log of the reflected voltage divided by the incident voltage. And also, the reflected voltage divided by the incident voltage would be the same number as gamma. In this example, the incident voltage is 100 millivolts, the reflected voltage is 20 millivolts. Therefore, the reflection coefficient gamma is 0.2. From there, the VSWR can be found either with the coefficient by itself or by using it to find the Vmax to Vmin ratio. Return loss in dB for voltage use 20 times the log of the coefficient or 20 times the log of Vmax to Vmin. For power, use 10 times the log of the square of that ratio. Note the return loss is always the same value for voltage or for power. Also, since the word loss is used, the resulting minus sign is usually dropped from the statement. In this case, we would say the return loss is 14 dB, not minus 14 dB. In RF circuits, efficient transfer of power from the output of one circuit to the input of another circuit is very important. Sometimes the input to a device is not well matched to its source. Designers must improve the matching to ensure the circuit performs as intended. One method of improving impedance matching is to insert a small value attenuator, maybe 2 or 3 or 4 dB, between the output, which is the signal source, and the input of the next stage, which is the source load. The return loss improves by twice the value of the attenuator, or in this example by 6 dB. and other passive devices have an associated VSWR. Therefore, every connection between circuits introduces at least a small amount of signal loss, referred to as insertion loss. As the signal frequency increases, the VSWR increases somewhat, and the insertion loss through the device increases. High-quality RF cables may be rated for 40 gigahertz, but they also may have 3 dB or even more insertion loss at 40 gigahertz. Over the years, I've found that best practices when measuring or adjusting instrument performance parameters is to avoid using more than one adapter when connecting cables and fixtures with different connector types. Using 2 or more adapters strung together in series greatly increases the risk of adverse effects on the signal level accuracy. RF adapters are available in dozens or perhaps hundreds of configurations and sold by many vendors. Finding adapters for your particular need will be quite easy. Noise. Noise is generated by virtually all electronic circuits. Resistors generate broadband noise even when no current is flowing through them. Heat energy is something that's always in the ambient air, and it causes random free electron motion in resistors, creating tiny voltages across the resistor, maybe microvolts or even nanovolts. Most of the noise in electronic circuits is called thermal noise, and sometimes it's also called Johnson noise or white noise. Semiconductors such as diodes and transistors also create noise as the electrons cross the junctions, and that noise is often called shot noise. Noise calculations and analysis is a complex subject that is beyond the scope of this presentation. However, for basic working knowledge, it's good to remember the 3 primary factors that affect the noise level in a given circuit or device. These factors are temperature, bandwidth, and resistance. Simple noise voltage calculations can be done if these parameters are known, and then adding Boltzmann's constant, which is a commonly used value in chemistry and physics. Some examples of how these effects are handled. For temperature, satellite receivers and amplifiers often have special cooling systems to keep their temperature well below zero. Keeping the components cold helps to minimize their internal noise. For bandwidth, designs include filters such as bandpass or low pass, and they're used to limit the noise level by reducing the circuit bandwidth. And for resistance, lower noise is one of the reasons the electronics industry chose 50 ohms for high-frequency devices instead of the 600 ohms typically used in audio circuits. Assuming all other factors are equal, the noise voltage is approximately 3.5 times greater for a 600 ohm resistance than it is for a 50 ohm resistance. Noise and dynamic range. All receivers and amplifiers have a range of input signals that can be processed properly without overdriving or getting lost in the noise. The upper limit could be the level at which heavy distortion occurs, but normally the standard for many receivers is called the 1 dB compression point, which means the point at which a 1 dB increase in input signal fails to cause any increase in the output level. At that point, the receiver input mixer level in commercial receivers. The difference between the optimum mixer level and the noise floor is called the maximum distortion-free dynamic range, or sometimes the maximum intermodulation-free dynamic range. Both commercial and consumer devices could use automatic gain and level control methods to keep signal levels within this optimal dynamic range. Signal-to-noise ratio is a common performance consideration in many electronic devices, like cell phones and radios. The noise has an effect on the signal such that the signal level is actually a combination of the noise and the signal. When the signal-to-noise ratio is large, let's say 30 or 40 or 50 dB or more, the signal level is unaffected by the noise. On the other hand, if signal-to-noise is less than approximately 16 dB, the signal will be artificially pushed higher by the noise. This effect is called the logarithmic addition of noise. For example, if the signal-to-noise is only 70 dB, the signal will measure 1 dB higher than its actual level. When the signal-to-noise ratio is only 3 dB, the signal level is actually at the same level as the noise. The noise is actually pushing the signal upward by 3 dB artificially, making it appear to be above the noise floor. This is something to bear in mind when measuring signals that are very close to the noise floor. Mixers. Mixers are used in a wide variety of receivers, from radios and televisions to satellite communication systems. One of the most common uses of a mixer is to convert a signal of one frequency to another frequency. Mixer circuits are often called converters. The typical mixer configuration is shown in this slide. The received RF signal is applied to one of the mixer's inputs. A signal from an RF oscillator, usually called a local oscillator, is applied to the other mixer input. The local oscillator and the RF signal are converted and they produce a number of mixing products. All of the mixing products are sent to the mixer output. However, usually just the difference is the desired signal. That is, the difference between the local oscillator and the RF input signal. That different signal is called the intermediate frequency, the IF. All mixers produce unwanted signals that must be considered, and usually they're suppressed with filtering methods. Three of the most common unwanted mixing products are harmonics, intermodulation, and images. As the applied RF signal increases, these unwanted mixing products also increase, sometimes at a faster rate than the increase in the RF signal. Depending on how they affect the performance of the system, these unwanted signals are often suppressed by sending the mixer output through a very narrow bandpass filter designed to pass only the IF while rejecting all other frequencies. Phase-locked loops. Phase-locked loops are used in a wide variety of commercial and consumer electronics devices. Some examples could be radios, cell phones, TV, GPS, DVD players, and many others. They can be extremely complex or relatively simple, but most all have four basic components: voltage-controlled oscillator, a reference oscillator, a phase detector, and an amplifier low-pass filter stage. In its simplest form, the VCO signal is compared to the reference oscillator signal, and any difference between the two signals is filtered, amplified, and applied to the VCO as a tuning voltage. The VCO is then tuned in the direction that reduces the difference to zero. At that point, the VCO is locked to the reference oscillator. Synthesizers. One disadvantage of a simple phase-locked loop is that the VCO has to be at the same frequency as the reference oscillator. Synthesizers eliminate this issue. Synthesizers are often very complex. The purpose is to allow the VCO to run at various frequencies within a specified range by using a divider. converts a sample of the VCO signal frequency to the reference oscillator frequency. Phase detector and amplifier produce a conditioned tune voltage that locks the VCO to the reference oscillator, but at a frequency that is precisely n times the reference oscillator. In this example, the divisor, or n, can be at any value from 20 to 40, which will tune the VCO from 200 to 400 megahertz while keeping it locked to the 10 megahertz reference oscillator. I hope you found this presentation informative and easy to understand. Thanks for watching.